this work is being done in collaboration with Professor Ajit here and others mentioned here. Uh, thanks to Shashwat, he mentioned briefly what is gravitational waves and how the waveforms looks like. So I'll just start off here. Um, so the most interesting source for detection of gravitational waves in LIGO and Virgo detectors are basically these compact binary systems, which includes like binary black holes, binary neutron stars, or black hole neutron star systems. And in the already completed runs like O1, O2, we have already detected 10 such binary black hole systems and 1 binary neutron stars. And the current run is going on for almost a year. And we have, I think, more than 50 detections already. So the detection of gravitational waves from these compact binaries have like gave us a lot of astrophysical informations. So for example, from these detections we have now a clear idea of like what is the masses of these binary components, these black holes, what are the spins, and what are the masses of the final black holes and spins, and all these informations which we did not have earlier. But so this is a picture of how this in spiral proceeds to merger and finally gives this. So this is for neutron star, but black holes follow the same in spiral and finally merges, and all the way they gives gravitational radiation. So one of the information that we have not been able to retrieve from these detections is that we don't have information about how these systems are actually formed. So we don't have any information about the formation channels. So I will try to uh, give some proposal like how we can actually uh, mm, probe this evolutionary history of these formations of these compact binary systems. So broadly, there are two categories of formation channels. So one is like binary systems of these complex objects are formed in galactic field. So in such scenario, they are formed with a very large initial separation. And if you apply Kepler's third law, then you see that they are formed essentially with a very small orbital frequency. And another formation channel is the dynamical formation, where these binaries are formed in a very dense system. And due to these interactions, it may be possible that they will in a bound system with a very small initial separation. And as a result, their initial frequency, orbital frequency will be high compared to the formation channel for galactic field, in galactic field. But the thing is that after their formation, they follow the same evolutionary path. And that is basically, so for example, in this schematic diagram, what I am showing is that, so let's see, sorry. So let's consider this one. So this one is formed in a galactic field with very small orbital frequency, and this one is formed in a dynamical formation. So in a very dense system like globular cluster, where the environment is very dense, and therefore initial orbital frequency is very high. But once they're formed, so initially let's say they have they have some eccentricity, but due to this gravitational radiation, this eccentricity will be lost, and finally they will be basically circularized. And this path is basically the same, which is basically due to Peters and Matthews, which says that if you have initially eccentric binary, due to gravitational radiation, your eccentricity basically decreases, and finally the orbit basically circularizes. So if we see here, so now gravitational detector like LIGO has a sensitive band which is above 10 hertz. But we see that both of these channels, these binaries, when they enters this region, their eccentricities are far below, let's say 10 to the minus 3. So even if we can measure some eccentricities, so if we have some capability to measure like eccentricity in this range, we will not find any eccentricity, because both the channels, for both the channels, the eccentricity have been decreased to a very small values. But if we go to a lower frequency range here, then you see that these binaries will have some residual eccentricity. And if we trace back, then we can say that these binaries have been formed in a very dense environment. So this way, if we can detect some residual eccentricity, then we can talk about their formation channel and distinguish between these two different categories of binaries. But the thing is, how can we actually probe this region? So I will argue that if we include higher modes, then actually we can have information from this region. So let's say, let me just explain what is these higher modes. So we know that these the gravitational waves are two polarizations, and conveniently they are written in this complex in terms of this complex uh, function h of t, and we can actually decompose this function in terms of spherical harmonics, where these are basically the gravitational waves modes. And this HLA mode have frequency which is equals to m times the orbital frequency. So we see that if our detector is sensitive above 10 hertz, then and we are detecting, let's say, 2-2 mode, then we can detect the 2-2 mode only when orbital frequency is 5. So when the orbital frequency is above 5, only then the 2-2 mode enters the gravitational enters the LIGO band. But if we include like higher modes, like let's say 8-8 mode, then if we have 8, then we can detect 8-8 mode for orbital frequency less than 5 hertz, let's say here. So the higher modes actually corresponds to lower orbital frequency. So if we include higher modes, then we have information of earlier phase of the binary evolution, and therefore we have information from the earlier phase of the binary. For example, in this plot, it shows the time until coalescence and against the orbital frequency. So when 2-2 mode enters, we have only few seconds before the merger happens. But if you consider 8-8 mode, then the time till until coalescence is very high compared to 2-2 mode. So we have this additional information if we include higher modes. And now one of the question is like whether we can detect actually these higher modes. Basically, because right now what we actually in the gravitational waves detection, we model the 2-2 mode only, because the 2-2 mode is the dominant mode, and other higher modes are basically few orders of magnitude smaller than the 2-2 mode. So let me just show how these amplitude of these different higher modes compare with the 2-2 mode. So this is a plot for assuming that the orbit is actually circular. So we see that the higher modes have very small amplitude power, small power compared to your 2-2 mode, which is the dominant mode. So if we want to detect, let's say, 8-8 mode, then you see that the sensitivity of the detector has to be very high. And another thing is that these higher order modes, enters the LIGO band much earlier. So if we want to detect the eccentricity, then actually we have to model these waveforms with some non-zero eccentricity. So if we add eccentricity in these waveforms, then this plot actually looks like this. So you see 2-2 mode has no effect actually, because when 2-2 mode enters the orbit has already lost most of its eccentricity. But as higher modes corresponds to earlier phase of the evolution, they have the imprints due to the eccentricity. So we see these fluctuations in the amplitude. So these are basically imprints due to the eccentricity. Now whether we can detect these higher modes. So these dashed curves are basically the noise sensitivity of the detectors. So this one corresponds to the LIGO band, LIGO detector, and we see that only 2233 or 44 may be detectable. But if we go lower, then it's almost, I mean, not possible for, let's say, this range of masses to detect these modes in the LIGO band. But if we go to future detectors like Cosmic Explorer, this one, this green dust curve, then you see that 88 mode or 77 mode is two orders of magnitude lower than this one. But we have to I would like to mention that the SNR, the signal to noise ratio, is basically integrated effect. So if we integrate over this range of from 10 to 1000 hertz, then this the signal will be like signal to noise ratio will accumulate, and it will give like more than one SNR. So this is a plot of SNR of each mode as a function of the total mass in the LIGO band, and we see that these 88 modes, if we want to detect the 88 mode, then the SNR of 88 mode uh, becomes greater than 1 for these total mass of about about 1000 at almost like 700 solar mass. So which is basically not very sensitive in our LIGO band. So if we want to detect like 50 solar mass, total solar mass to be 50 solar mass, and we detect the higher order modes in LIGO band, then it's not possible. But if we go to Cosmic Explorer, which is a future generation detector, then we see that SNR, the signal to noise ratio of 77 mode, let's say this one, becomes greater than 1 at about 50 for m equals to 50 solar mass. So the key point is that in future detectors, we can detect the 88 mode for 50 solar mass total mass in the Cosmic Explorer. And if we can detect these modes, then basically we have information about the eccentric evolution of the binary. And if we go back to this plot, then we see that if we have information from this range, from this frequency range, then basically we can measure some residual eccentricity, and that will basically give us information about their formation channel. And if we don't detect, then we can put some constraint on the formation channels. So, so there are further works to be done. This is an ongoing process, ongoing work. So that's it. Thank you.
Thank you, Arif. If there are any questions.
About this plot.
Yeah.
So it's very important because this is what you're using to distinguish between the two formation channels, right? So how do you see that like the eccentricity for galactic field formation like channel is like different at different orbital frequency from dynamical formation channel? Like how do you get these plots?
No, so in actual scenario, there will be a, like distribution of eccentricity, initial eccentricity and initial frequency. But broadly, you can separate. I mean, there will be much more black holes in a dynamical situation, which will have small frequency. So in actual case, there is a distributions, but you can there is a, I mean, distinction.
Just a quick question about the plot where you showed the Fourier transform and the noise curve. What are you taking a specific inclination? Is it the optimal
No,
inclination?
this is the individual modes only. It's not summed over anything. And so inclination is like so basically 0 if you want the answer. It's like the optimum thing you can have.
I see. It is optimal. Right. Right. Okay.
I had a question about the distribution graph again. So
This one.
this one, yeah. So is the statement that for the galactic field, the ones that are formed from the galactic field and the ones that are formed from dynamical formation, the distributions are really separated in both orbital frequency and in eccentricities?
Yeah, so even if you have like distribution in eccentricity, does not matter, as you say. I mean, there will be, but the important fact would be that the distribution in frequency.
So they're really separated. And
Yeah, there is a clear separation.
there's some reason why?
That is because in dynamical formation scenario, the environment is very dense, so you have much more interactions. So maybe there is a binary, but there could be a third let's say black hole, which can actually interact with the existing binary, and one of the component may just get ejected, and they will form a very close orbit. So that compact binary will have a very small separation, and that's a very small initial frequency. Sorry, large frequency.
And somehow there's no intermediate. We haven't.
Yeah, there may be, but so if you see the distribution, then the dense region will be like here, and there will be a dense region there. There may be some overlap, but those will be not dense.
Thanks.
So we'll thank Arif with a round of applause. And